primary problem with this launch is whether or not these O-rings that are essential in preventing hot gases from escaping and prematurely igniting the rocket fuel is whether or not they will perform reliably at the launch conditions given that they are sensitive to temperature. We are constrained by a few things regarding money, time for rescheduling, the temperature at the launch, and the material properties of the O-rings themselves. If we assume that the temperature at the launch will remain stable at 60 degrees and will not change during the countdown, we will also assume that the data about the O-rings based on past experiments applies to this specific mission as well. O-rings do not seal effectively below 55 degrees, and with the expected environmental temperature of 60 degrees at launch, the margin of error is way too small, so we decided that we should not proceed with the launch, or at least delay it until the temperature increases. This would be best according to material properties of the O-rings and according to past historical data with past launches. If we were to proceed with the launch, there could be a major consequence greater than economic costs or rescheduling problems. In terms of the data, O-rings are typically made from elastomeric materials, which behave like a combination of a solid and a fluid, meaning that they're able to deform under pressure and return to their original shape. So it has elastic properties. These materials are very flexible, making them ideal for sealing applications where they need to create a tight seal between different components, such as the boosters or fuel lines. However, the flexibility of these elastomeric polymers is highly dependent on the temperature. At normal temperatures, elastomers maintain their flexibility and can easily compress or deform to fill different gaps between different surfaces. As the temperature decreases, these elastomers start to lose their flexibility, and this is due to the molecular structure of the materials themselves. Elastomers contain a long chain of molecules that can stretch or move past each other when warm, but as the temperature drops, these molecules lose energy and their ability to move freely, which causes the material to become more rigid and less elastic. This process is called the glass transition. At or below the glass transition temperature, the elastomer becomes very brittle and it can no longer function as effectively because it cannot take the required strain or compression on the O-ring itself. For a lot of these elastomers that are used in O-rings, this transition point starts to occur between 55 degrees or 60 degrees. So that would mean that for this O-ring that we're using for the launch, it would become very unreliable below that threshold. These O-rings are primarily responsible in preventing high pressurized gases from escaping the fuel system. If the O-rings do not form a tight seal, the fuel could leak, leading to a possibility of an explosion. If we were to look at the Challenger disaster, the O-rings in the solid rocket boosters were unable to maintain the flexibility, and in these cold temperatures, it led to a failure in the seal. This allowed for the gases to escape, which ultimately caused the booster to blow up. In different real-world launches, O-rings exhibit signs of failure when exposed to temperatures below 53 degrees, and in some cases, partial O-ring failures were noted at temperatures around 58 degrees. This real-world data shows us that even temperatures slightly above 55 degree threshold, there is a major risk of a partial failure, thus leading to dangerous outcomes.
The decision to delay the launch could cause significant issues, including the cost of the mission, rescheduling personnel, relocating resources, and potentially losing a launch window. Additionally, the cost of delaying the mission would include operational overhead for NASA, as well as a missed opportunity in terms of scientific research and satellite operations. However, these costs must be weighed against the potential economic and human cost of a failed launch, which would result in the loss of the mission, costly investigations and repairs, and not to mention the risk to human life if it's a manned mission. From a Christian worldview's perspective, human life is sacred, and prioritizing safety is extremely important. Ethical decision-making in this case involves weighing the potential risks to human life against economic or scheduling concerns. The Bible teaches stewardship, implying that we are responsible for the well-being of others and the responsible use of resources. Proceeding with the launch, knowing there's a chance of failure, would compromise our ethical responsibility to protect human life. A Christian ethical perspective would advocate for erring on the side of caution, even the possibility of endangering lives cannot be justified. While the forecasted temperature of 60 degrees Fahrenheit is technically above the minimum threshold, given the critical role of O-rings in sealing pressurized systems, launching at 60 degrees Fahrenheit leaves too small a margin of error. O-rings lose their sealing capability below 55 degrees Fahrenheit, and historical data, including the Challenger disaster, shows that cold temperatures can lead to catastrophic failures. While delaying the launch may result in economic costs, the risk of proceeding, including the potential loss of the mission or human life, far outweighs these concerns.
Here's a table of how the O-rings performed in the real world. With the Challenger STS-51L launch, it was 36 degrees Fahrenheit, and the O-ring had complete failure, which resulted in an explosion. Columbia STS-61C was 58 degrees Fahrenheit. Erosion and slight blow-by is how the O-ring performed, and the outcome was successful, but with still some issues. The 7th Challenger STS-51B was 75 degrees Fahrenheit, which had ideal performance, and the launch was very successful.